Bismillahirrahmanirrahim. So we start chapter 9, which is about virtual memory. Chapter 8 was about main memory. In the main memory, if you remember, we studied about organization of processes into main memory. And the concept there was that if you bring in a process into main memory, we studied different techniques. One was the contiguous memory allocation. Okay, so you have one big chunk which would contain the whole process, one big chunk of memory that would contain the whole process, the entire process at the same time. Then we divided this process into pages and we load each page into any available free slot, which is known as a frame in the main memory. Okay, but again we would load the whole process, the entire process at the same time in the main memory. So that's what we studied in chapter 8, that we would load all the pages at the same time into main memory. Now in this chapter we build the idea of virtual memory. It means that we can have the possibility not to load the entire process at the same time into main memory. And why would we do that? Because it will give us different benefits. First, you don't need to load the entire process into memory because you may not need all the process functions or all the code at the same time, or maybe some code you don't need at all. For example, in some process there may be some code related to error handling. This code will be executed only when there is an error. And let's say this program executes, there is no error, the program finishes. Okay, so the error code is not executed at all. And if we don't need the error code, then why do we load it into memory? So we can save some memory space by not loading the code that we don't need. Similarly, there may be some other functions in the program, or routines, we call it routines, which may not be needed normally, so we don't need it to load them into main memory. Example is, let's say we need some printer functionality in our program, but the user may not need the printer code all the time, which means that maybe user loads a program, run a word processor for example. Okay, so the word processor has the printer function, but the user may not need to print the document. The user may just edit the document and quit the program. So why should we load the printer functionality into the RAM? And lastly, there may be some data structures which are very large in size. So instead of loading the complete data structure, we may need only part of it. No need to completely load the data structures. So it means that the entire program code may not be needed at the same time, and we can load only partial program into the RAM to be able to execute it. This can have several benefits. First, because you are loading only part of the program, so it will be efficient to load that instead of loading the whole program. That will take more time because you are loading the program from the hard disk, which is a slow process. So loading only part of it will actually result in better memory loading, faster access. It will also result in improved CPU utilization. Why? Because you are loading only small part of the program, so you can load many programs at the same time. So increased CPU utilization, increased throughput, which we desire, but at the same time there will be no increase in the response time, and there will be no increase in the turnaround time. And these are the things we don't want to increase. We want to minimize the response time and we want to minimize the turnaround time. Just think about these criteria. Why will they increase or why will they not increase? Okay, the solution is there in chapter 6, and you should understand even from your assignment which you are going to submit, you have questions about the turnaround time. So the conclusion about this slide is that if we have the ability to load only part of the program, it can result in various benefits. And also another concept here is about virtual memory, which means that we can see the logical memory of the program different from the physical memory. In physical memory, you know that we have frames, so you can load any page anywhere. But the logical memory has the added advantage that because you are not loading the entire program at the same time, so we can have very big programs, large program sizes, which are larger than the available physical memory, but still you are able to execute it because you are executing it in parts. It will also allow to share the address spaces by several processes at the same time. That is an interesting fact, we will see in the next slides. And more programs can be running concurrently and less I/O is needed, etc. So the virtual address space, which will be result of the virtual memory, is the logical view of how the process is stored in the memory. Normally we have seen before from previous chapters that logical address spaces for each process, they will start at the address 0 and they will keep incrementing each number, for example 0, 1, 2, 3, 4, etc., until the end, which is the size of the process. But the main memory is organized in page frames, and we need the memory management unit to map these logical addresses into physical addresses. So one of the techniques that we are going to study here is the demand paging. There is another one, demand segmentation, but we are not going to study. So we are going to see how do we implement demand paging. Before that, we have this diagram which shows the idea of virtual memory. So your virtual memory is in fact your logical memory, which now consists of pages in a sequence starting from page 0, which contains the address 0, until some page which contains the last address of your program. And this virtual memory is mapped to physical memory using a memory map. So each page is mapped to physical memory, but interestingly you can also see that some pages, for example here this page, has been mapped to a page in the baking store. This page is not available in the physical memory, but still the program can use it. How? This is what we are going to study. Now, a benefit of virtual address space is that we know each process has 4 parts: the code or the text part, the data part, the heap part, and the stack part. The heap and the stack, they are going to increase their sizes as the program runs or even decrease. So there is some free memory required, which is in the form of the hole between the stack and the heap. Now how much free memory will be needed, it depends on different situations, depends on the data structure, etc. But if you allocate more memory and you don't use it, it's a waste of memory. So we can use the virtual memory to address this issue, which means that we don't give much memory to heap or stack in advance, but when there is a need, we will use the virtual memory to allocate it into these spaces. This way we can also implement the shared library or the system libraries. So for example, you can include a shared library in 2 programs, as you can see here, and this shared library is implemented as pages into the virtual memory and is being referenced by each of this process using pointers into the virtual memory. Now, as I told you before, what we need is the concept of demand paging, which means that we will load only those pages which are needed into the RAM. So the idea is that although we can bring the entire process into main memory at the same time, this is not desirable, this is waste of space. So we will bring only some page into memory when there is a need for that page. And this is the concept of demand paging. Demand paging means that you load a page into main memory when there is a demand for that. So when is there a demand for a page? There is a demand when you need to execute an instruction from that page. So the logical memory of program, when the program is executed, the CPU will generate the logical address. This logical address is converted into physical address using some memory mapping technique, and this physical address is actually found in some page. Now, as I told you, when we implement demand paging, we see that if this page is not yet loaded, we will generate a demand for that page and it will be loaded into main memory. So we have already seen that by implementing demand paging, we will need less input output, we will need less memory, the response will be faster, and because of small memory required for each program, we can load many programs at the same time and we can support more users, because maybe we have multi-user systems, so different users are using the same memory, so we can accommodate more users. So this concept of loading a page when there is a need, this is same as the swapping. If you remember, we studied swapping before. So in swapping, when there is a need of memory for a process, so you swap out some process, existing process, and you swap in the process which you need. So similarly is the case that when you divide your virtual memory into pages, and when a page is needed, you make a reference to it, you check if that page is available into main memory. If it is available, you use it. Otherwise, if the reference made is invalid, you will abort your operation, which means that the reference is made to a memory area which is not in your memory address space, so you abort that process. Or the third thing is the reference is valid but the page is not in memory, so you bring in the page to memory. Now the process which brings in the pages to the memory is known as a pager. It is like a swapper. But in this case, in case of demand paging, the swapper is a lazy swapper, which means that it will only swap a page when there is a need for that page. So if a page is not needed, it will not swap in to the main memory. So these are some of the basic concepts of paging, which is similar to swapping. So when you swap in a process, the pager may guess which pages will be used before swapping out again, because if you swap them out and you need them again, this will be additional process. And to determine those set of pages which will you will need again, then actually you will have some functionality into the memory management unit, and demand paging can be achieved only if you have some additional information about each page. So if the pages needed, they are already in the memory, okay, then there is no need for demand paging, because it's the same thing. You just access the page and you load its instruction into the CPU. However, if a page is not memory resident, which means that it is not in the memory, it is into the virtual memory or it is into the hard disk, then the first thing is you detect this thing that the page is not there, and the second thing is you load the page into memory from the storage. The advantage of this technique is it will not require any change in the program behavior. Program will execute like before, and also there is no need for the programmer to change the code of the program. It is all managed by the operating system. Now the concept is which page you will need to bring in and which page you need to bring out. So for that we introduce another bit, which is valid-invalid bit, into the page table. Before we have seen the page table, it is just a mapping from a page number of a logical memory to a frame number of physical memory. But this time we are adding one additional bit in the form of valid or invalid bit, so it can have a value of V or I. If the page you need is already loaded in the frame in main memory, then it means that is a valid page, so you will have the value of the bit as V. But if the page is not in the memory, then it will be an invalid bit set for that frame, which is referenced by the page table. Now, during the translation of logical address into physical address by the MMU, if the MMU finds that the entry for some frame number is I, then it will generate a page fault. What is a page fault? A page fault means that the page needed by the process is not in the main memory, and the operating system must load that page from virtual address into the main memory. Now here you can see the diagram which shows this mapping technique, and here are 4 components. On the left you have logical memory. Then this logical memory has 8 pages from 0 to 7, okay, for a process which has these pages. Then there is a page table which does the mapping of these pages into frames. For example, page 0 is in frame 4, page 2 is in frame 6, and page 5 of the process is in frame 9. So page 5 is actually this content F. You go into frame 9 and you will find the F. And finally you have this backing store, okay, from which you load these pages initially. You can see that the process is loaded from the backing store, so the backing store has all those pages from A to H there, and a copy of these pages is loaded into the physical memory. Now the thing in page table is that those pages which have been loaded, here the example says 3 pages, page A, page with contents A, page with content C, and page with content F. These 3 pages have been loaded, let's say when the program starts. So you can see that the valid-invalid bit is set to V for these pages, and the remaining pages which are not yet loaded, for them the valid-invalid bit is set to I. Why is this important? Because if you make a reference to this frame number, page number 3, which is not there, so the operating system must know that it is an invalid page and it must not read anything from here. But if there is a need, so it will generate a page fault to indicate that we need to load this page content D from this backing store into the memory in some frame. So whatever frame is allocated, it will be shown here, and this valid-invalid bit will be changed to V. Now we have already discussed about page fault. Page fault means that if you make a reference to a page, for example page 3, then you find that there is an invalid bit, so this page is not present, and that is what is known as a page fault. The operating system will generate a trap, okay, in fact the program will generate a trap to the operating system. This is known as the page fault trap, and the operating system will see that the page is not present, so it will load that page into memory. Where will it load it? It will need to find a free frame, okay, and will need a disk operation to load the page from the disk into the free frame. Once the page is loaded into the free frame, it will change the valid-invalid bit from I to V. Before it was I, it was invalid. Now it has turned to V, and then it will restart the instruction that caused the page fault, which means that when a page fault is generated, this is an important point, please understand. When a page fault is generated, the page is not there, so the operating system temporarily stopped executing the process. The instruction which generated the page fault, it is indicated, it is identified when the page is loaded and its valid bit is set to V, so the same instruction is executed again. So this instruction is executed for the second time, but this time because the page is already in the memory, so page fault is not generated and the process executes as normal. Now this diagram shows all those steps to handle a page fault by the operating system. So in step 1, you see that in this page or this area of code, it needs this module M, okay, to be loaded. For example, this is some instruction, so there it makes a reference to this page which is not there. Actually it is invalid, so a page fault is generated using a trap to the operating system, and the operating system goes to the backing store, finds the page and loads it into some free frame which it finds, any available free frame, and then this missing page, it comes into the free frame and the operating system updates the page table. So this page which was missing, now it is here, the frame number is written and the valid-invalid bit is set to V, and finally the instruction is restarted from the same place. The same instruction is re-executed which was executed before and resulted into a page fault. Now this whole process is known as demand paging, which means that you load a page when there is a demand for it. So there are a few aspects of demand paging that we need to understand. In extreme case, when you start a process for the first time, so you can see that no page is there in the main memory. The page table entry will be empty and all those bits, valid-invalid bits, will be set to I. So what happens is that instruction 0 is executed. There is no page that contains instruction 0. A page fault is generated and the page is loaded into memory. After a few instructions, another page is needed. Okay, the operating system sees the invalid bit for that page because the page is not a resident, it is not in main memory. So this page is loaded again, and in this way, in the beginning, many page faults are generated very quickly. This is the idea of pure demand paging. Okay. Another thing is that a given instruction could access multiple pages at the same time. So there will be one instruction, but it may be referring to a page for some data, another page for another part of the data. So at the same time, in one instruction, many page faults will be generated. And when all those pages, they are loaded into the main memory, this instruction will be executed. So in both these cases, you can see that the number of page faults is quite high for any program. And to implement this thing, we will need support from the hardware, which means that the table, the page table, it will have valid or invalid bit. Also, you will have the secondary memory with enough swap space to actually support this paging. And thirdly, the support for restarting an instruction to see that when an instruction results in a page fault, it will be kept as silent, okay, and when the page is loaded, it will be restarted once again. So these aspects of demand paging must be considered when we design a system that supports demand paging. Now, one problem that can occur is the issue that when more than one processes, they share some page, for example parent-child or any other ways in which you can share memory, which is essentially sharing the page. So if more than one processes, they are sharing the page, and in case there is no need to modify the page, all the processes, they are just reading the data from the page, then it's not a problem, okay. All of them, they can share the pages without any error or without any modification. But in case if one of the process needs to modify the page, then actually it can create a problem for the other process which is needing the older data. So two processes or more than two processes, they are acting on the same page, but one process needs to modify the page. We need to create a copy of that page, because whenever you want to make to modify a page, you would not allow that page to be used by any other process. So you will create a copy of the page, and the process which wants to modify the page, it will be working on the copy of the page. So the other processes, they can still use the same the same page. So here is the example. You have two processes, and they have three pages, page A, page B, and page C, and both of these processes, they are using all these pages at the same time. Now here in this diagram, we assume that the process 1 wants to modify page C. So before modification, it looks like this, that process 1 and process 2, they both have access to the same page C. But what happens is that if the process 1 modifies page C, so we will firstly create a modified page of page C. We will create a copy of page C, and then process 1 can modify the copy of page C without affecting the original copy. So which copy will be the correct one, the valid one? That is to be decided later on, and that will be actually sent back or written back to the hard disk. Now we know about the concept of demand paging, we know about the concept of copy on write, okay, which is this example shown to you here. Now we will see the case when the operating system wants to bring in a page into a free frame, but it finds that there is no free frame. So what will happen? Why could this be? I mean, when can there be a situation when that the operating system does not find any free frame? It can be because that the different processes in the operating systems, they have already occupied the entire memory, so there is no free frame. Or maybe the kernel or the IO buffers, etc., the operating system components, they have occupied the memory. So at the end, we are not left with any free frame. So because we need to bring in a page, we must find some frame for that. And one solution is that if there is no free frame, what we can do is to find a page that we can replace. We can use that page for bringing in the new page instead of that. So the thing is, we will need an algorithm for that, which will replace the existing page in a frame by a new page which is needed to be executed by the CPU. So what should the algorithm do? Should it terminate the process, the existing process, whose page it needs to replace? Should it swap out that process or that page? okay, and replace the page afterwards. And such an algorithm we need from it the performance so that it can result in the minimum number of page faults. Okay, a thing which we need to consider is that, let's say if you replace a page, you take one page out from the main memory, you swap out, maybe after a few instructions you need that page again. So will you keep swapping out and swapping in these pages like this, or will you have a smart algorithm that can choose only that page which you may not need in the near future? We can also make an improvement to have a bit which is known as a dirty bit or modify bit with each page, which will help us in determining if this page has been modified in the RAM or not. Why is this important? Because when we make a replacement, so we need to write the page from the main memory into the hard disk. But if we see that the page has not been modified, then we will not write it in the hard disk, we will just overwrite it by the other page. So the modify or the dirty bit will help us in determining if we need to write a page into hard disk or we just replace it by the other page without making any changes. So that will make it faster, because writing something onto the hard disk, it takes time. So here in this example you can see what we have is that you have logical memory for two users or two processes, okay, and the program counter is currently in logical memory of user 1 in page 1 and executing some instructions that requires to load page M or load M, which is contained in page M. Now if you can see, this is in page this is page 1 of the process, okay, and if you go to page 1 of the page table for that user, then right now it contains reference to page 4, which is valid, and page 4 frame 4, you can see it is containing this load M instruction, which is totally okay, but M itself is not in the page table, or it is not in the main memory, so you have to load that M. So where do you load it? That is the point. In the page table for user 1 there is of course empty space, because the page table has the same number of entries as the process, but it says that this is invalid, okay, so the last frame it is empty. We need to, because the last frame it is referring to M. So let me repeat it in another way, okay, because maybe I was not clear, that the program counter needs to load M, okay, this is the instruction, and the load M is going, this is going to load this M, which is the page number 3. But page number 3, if you see here, it is invalid because it is in the hard disk, not yet here in the RAM. So we need to do this to replace any of the existing page, because these frames, they are all occupied. So we will choose one in which to load this M. Similarly for B, user 2, we can see that here the page 0, page 2 and page 3, they are valid, but page 2, which is content B, it is invalid. And if we are going to load it, where we are going to put this in, so we will need for replacement of a page. Now the basic idea of page replacement is that we will first find the location of the desired page on the disk which we want to load, okay, then we will find a free frame in the main memory. If there is a free frame, we will use it and load the desired page. If there is no free frame, then we will find a page to replace by this new page that we want to load it, and this page will be located into some frame which we know, which we will call as the victim frame. So it means that in order to load a frame into in order to load a page into an existing frame, we will need to find a victim frame. And this victim frame, if we are going to be replaced it by a new page, we will also make sure that if it is not dirty, we can just replace it directly. But in case it is dirty, then we will need to write it into the disk before being replaced by the new page. So we write the victim frame to the disk, then we bring in the desired page into this free frame, which was the victim frame, and update the page table, okay, to refer it to this as the valid page. We will set the valid-invalid bit to V. And finally, we will continue the process by restarting the instruction that caused this trap, as I discussed before. So this page replacement will look like this. Okay, in step 1, you see that you need a page to be brought in. Okay, so you see that this victim page is a dirty page, so you swap out victim page onto the hard disk. In step 2, you see that this is frame F. So for frame F in step 2, we will make it invalid in step 2. Okay, that this is invalid. Then we will swap in the desired page into frame F. And finally in step 4, we will make it to V, that this becomes a valid page. Now the page replacement, in this example we choose a victim frame, but how do you choose a victim frame? Which frame will be victim? Because you can have 1000 frames. So the selection of victim frame is actually dependent upon the type of algorithm, which we call as the page replacement algorithm. How do these algorithms work? That we will study in the next lecture. For now we will stop, and in the next lecture we will start with the page and frame replacement algorithms, and we will study how do they work. So inshallah we stop here now.